So there is a limit to that. But however, these three surface states actually, they are so one can see that this one possibility is just straight up. That's like bismuth selenide. So it's topological right away, spin polarized. And this bismuth antimony is actually, it realizes more what Kane had predicted, this partner switching behavior. So partner switching has this zigzag pattern, but there's nothing religious except for the Kramer's theorem. There's nothing religious what should happen in between. So what is happening in bismuth selenide is that this guy goes up, and then it does this, and then it goes up. So it's actually one state. So the bismuth antimony has one band that carries the topological index. There is further check. Now, okay, and this is the beauty about the difference between geometry and topology, that topology only cares about connectivity, geometry doesn't. So these are topologically equivalent. So that means bismuth antimony realizes a partner switching surface state, whereas bismuth selenide doesn't do that. Now, I want to check this scenario without, now I want to totally get rid of the alloying disorder. Okay. It's straightforward to calculate the band structure and prove that there is no inversion between insulator and the semi-metal. And semi-metal, pure antimony carries the Z2 number, it's just parity, even my students can do that. Okay, so now if I look at pure antimony, no disorder, then this is the structure, surface structure. This is where the bulk band has valence band heads up. So there is intensity there, it's degenerate with even if there is surface state. And this is, again, this is also partly degenerate with the bulk state. Antimony is a semi-metal. There should be electron hole population at the Fermi level for the bulk compound. Only pure surface state in antimony is the central Fermi surface. So and again, we did all those KZ and all sorts of things to confirm that. The topological surface state, again, what it looks like Kane's picture, that there's only one. However, so this is the schematic picture, what is happening. So this stuff you see is related to that, and this stuff is related to that. So these are bulk states. So the surface structure is that the Kramer's point is down here. So there is, unless we can raise the chemical potential up here somehow, we cannot make it, even if we raise there, the states are there. There is no way to introduce a gap. No way to have a single pure surface state and insulator. So antimony, although it is like this, but it does not, band structure does not allow you to realize that state. Now I want to look at the spin polarization on the surface. And okay, so this is just a more cartoon that these states, even if they are surface-like, they're resonant because they're degenerate with the bulk. And what happens in antimony is that from Kramer's point, it connects up here. So it's like bismuth selenide, except that it's a semi-metal.
Is the spin assignment known from the band structure calculations?
Spins, you mean the...
Which one is up and which one is down is known from the band structure.
Right, yeah. Okay.
I put it in the survey state.
But that was just a type finding calculation. Using the...
Oh, this is Kane's calculation. I mean, T.O., Fu, and Kane.
So it's just there's nothing sophisticated. It's just using the type finding model.
Quantization accuracy is always same.
Huh?
Quantization accuracy is always same.
Well, I mean, that's what I'm trying to show here. So the nice thing about antimony is that the states at higher momenta, they don't matter to determine their Z2 number because they're degenerate with bulk anyway. So they're they're irrelevant. So near gamma points, spins are in a spin-orbit coupling system. The spins are better. It retains more polarization than away from the K at a high momentum. So here we are lucky. We do a scan, spin resolve scan. So this addresses your question that now one can see that it's much nicer. Polarization curves are much nicer. So, we look at 30 millivolt because at Fermi level its intensity starts to drop. But assuming that, it confirms, but looking at here, nothing has happened to the band, so we are safe. So I can take these cuts on this central Fermi surface along different lines and look at the relative polarization of the spins in my spin detector. So up, down. If I take a cut, it's up, down, like that. So that means it rotates like that. There's a left-handed rotation. And from that, since the other part of the spin-orbit split band, it's degenerate with the bulk, and it does not enclose any trim, it's irrelevant. I'm left with a single spin-polarized Fermi surface where the spin rotates. So there is straightforward, I can now get the angle, it's close to pi, so there's a pi Bery's phase on the antimony. Okay, now I'm going to summarize the surface structure using cartoons on bismuth antimony and antimony. In pure antimony, it's straightforward, Kramer's point is there, and bismuth antimony, if you dope the surface, then you are also single band. The spin down band goes there, and then it goes through a partner switching, just like this picture. Although, there's nothing religious that it has to go like straight. It does not violate any. It's topologically equivalent. One nice thing about these surfaces is that they have this mirror Chern number or something. The bulk has the mirror Chern number, which is reflected on the surface, that the spins rotate in a certain direction. Okay, so it's a very complicated story, and we have been spending a lot of time and energy to really sort out those details. At the same time, I involved two of my students, not David, who worked on the bismuth antimony, Matthew and Dong, to work with Kava to find a new set of materials where possibly we can have a simpler picture, more like what Kane has drawn in his News as Views article for our paper. Like, can we get something like this? And it turns out we can. And it shows up in bismuth selenide. So in bismuth selenide, nice thing is this is down, this is up, so there's a large gap. So it's like that. And if we do the experiment, we can see the Kramer's point intact. And the challenge is that it has vacancies, so the Fermi level is up. But it is nice from the point of view that although Fermi level is up, this is for the first time we're imaging the entire surface state of the undoped compound. Spontaneously, it came for free.
So is it an indirect gap semiconductor?
It's direct gap.
So,
No, there is actually it's not correct. It's not. This schematic is not.
Is it intrinsic though? The Fermi level intrinsic, or is it?
It's whole. We believe it's vacancy. Yeah.
So in different samples, do the
Yeah. So that's the nice thing. If we use samples from one batch to another, the Fermi level moves up and down.
So they are all electron doped?
Yeah, they're all electron doped.
And how much is the peak Clay concentration?
It's actually low. This it's in my preprint. Somehow it's not in my talk, so I drew it here. The Fermi surface is a tiny one. It's like 5% of the Briand zone. So this is another advantage. That.
And what about the bulk? I think he's asking about the bulk, though.
Oh, you mean the bulk? Bulk. You mean the bulk? No, we haven't.
Around 10 to the 18.
It's around 10 to the 18.
A very, very simple decay.
Okay, it's around 10 to the 18 as sample dependent.
It's like heavily doped.
Okay, so we have this picture. It's the Kramer's point, which is, if I look close, it should look like Dirac point. And since I'm hitting part of the bottom of the conduction band, I also have resonant state. And that resonant state is sample dependent. Okay, so then we tried to do what Shu Chang has suggested me to do. Well, not on this compound. He suggested me to do that on bismuth antimony, but I realized this could be more interesting. So put a layer of magnetic atom on the insulator and see what happens. So when we did that, deposit a monolayer of iron, two things happen. One is that those
control to the level that it's a monolayer?
It's submonolayer. No, we do not control to the level of monolayer.
We just count the actual.
Yeah. Actually, it's even more simple. We just count the dose.
Uh-huh.
It's more primitive. Okay. So one can see that there's a very nice protected Kramer's point there, and then when I put iron on the system, then I see two things. One, actually, it's better from the raw data that it became parabolic, and then it opened a gap, and that's one thing. Huh?
How large is the gap? About?
It's hard to. I mean, it's 0.1 or so.
So this is
Other size.
And then the second thing that happens, which we cannot control, is that it also dopes the system. So the Fermi level is rise. So now what has happened in this picture, although it's not insulator anymore, so I have valence band, so this answers your question that my schematic was wrong, because you can see from the raw data, it's a direct gap, not indirect gap.
Direct surface gap.
No, this is bulk. I'm imaging both surface and bulk. So the surface part is tangential to the bulk. So that's what I'm trying to draw here. So when the Kramer's point is protected, it looks like this. So when when we put iron, it looks like that. It opens a gap. But the nice thing here, iron, well, in a sense, it's also
donating electrons.
It's donating electrons, yeah. And what is happening is that it's donating a lot of electrons. That's something we cannot control. But it's from theoretical or conceptual point of view, for the first time, I mean, many of us have seen this thing in the theory literature. For the first time, we're imaging that. That's the interesting thing to me. Huh?
Principal group also did the magnetic field experiment.
Yeah, but not the direct imaging of the band structure.
When you dope iron on it, it's paramagnetic?
We haven't characterized all those details.
But this is with the internal magnetic field or without?
We just deposit some iron on the surface without external magnetic field. Yeah.
So you don't know